Good morning, everybody. This is a real pleasure to talk about this topic that is a subject of research that I've been working on in the past several years. And this particular one, which is a pressurized feeder for biomass injection into gas-solid fixed and fluidized beds, has been done with a postdoc researcher that came to IFP, and we worked on it for a couple of years. So just to start with the motivation, we know that we have discussed this also at Pressurized meeting. Waste biomass is a valuable feedstock for thermochemical processes such as pyrolysis, chemical looping combustion, gasification, and so on. But feeding biomass into reactors is pretty difficult, and that was also indicated in this paper here. And that's because of the unusual physical properties of the biomass, the wide size distribution, the shape, moisture, that makes it very difficult to inject. But we know that the performance of the conversion is directly related to how efficiently we can inject this biomass into the reactor and without any clogging and continuously in a reliable way. For those of you that were here and the talk of Carl Jacob on pneumatic injection is an interesting way to inject the biomass into fluidized beds. So that was the motivation, and for that one, we built a pressurized pulsed feeder for injection, a pneumatic injection of a batch of biomass, and this is of specific importance for studies where, for example, we want to do the kinetic study of the combustion or gasification of pyrolysis of biomass, and we need to inject just a batch of particles inside the unit in an efficient way. Or when we do hydrodynamic studies in cold flow models, and in that one also we need a tracer that in a batch mode we want to inject into the reactor. So we studied this, one for doing a hydrodynamic characterization of this kind of transport of pneumatic injection of batch biomass into the reactors. We did some experimental hydrodynamics just as part of the transport, and then we did also penetration. I'm just going to focus on the transport of this biomass, and the penetration I will show it maybe in future. So in this presentation, I'm going to first talk about the experimental part, how the transport of this sawdust is related to the operating parameters, biomass properties, and downstream conditions. Is it a fixed fluidized bed, or is it just an empty bed? And then the part that I really like is the comparison, once we do with numerical and experiments, and how we then use these numerical simulations of Barracuda for extrapolation to other conditions, or scale up or down. Okay, so I start just to show you the experimental rig that we had. This is the main column, which is a fixed or fluidized bed. And this is the injector that we used. It's made of two sections. As you can see here, there's a ball valve that separates this part, which we call pressurized chamber. We insert a certain amount of biomass, which is indicated with this packed bed with a mass of M. We use this pressure to pressurize this part. Once we open this ball valve, the pressure that is built up here is going to push this biomass into the main column, and we could use also secondary air injection. We placed a fast camera in this region here, as you can see, in order to see the dynamics of the transport, and also to measure the time that the biomass needs to get. So here's the video that we have at 3,000 frames per second. You can see that we have just depicted different phenomena of this transport. Very dilute region, then we get to the more dense regions with some voids in it, and then there is a big plug of solids that is being transported here, and that's where actually most of the biomass is being transported to the unit. The pressure actually, once at the beginning it accelerates the particles, but then there's a tail of particles that are remaining. We can see that the particles start decelerating here because the pressure is actually being balanced in the entire line. And at a certain point, as you can see also here, that we have that there is just a few particles that remain in the injection line. So by considering this phenomena here and doing some image analysis with our postdoc researcher, we were able to understand what was the time that the biomass was actually being transported and being injected into the unit. and to get the solid mass flux. As you can see here, at a certain point, once the driving force is being completely dissipated, the particles actually start doing some recirculation here. At this point, we considered that the transport was finished, and we measured also the remaining amount of biomass that was negligible. It was just less than 1% of the initial mass. Okay, so we did this, and then we started studying the experimental part with different operating conditions. We operated this chamber with pressures between 180 and 500 kilopascal, different masses of particles. We use or not the superficial gas velocity for the secondary injection in order to enhance the injection. We use different kinds of sawdust with D50 between 440 micron and 1,000 micron. We injected the biomass into a single phase unit just with air, or fixed and fluidized bed with different superficial gas velocities. This was done, and we wanted to see, we published just these dynamics in terms of hydrodynamics in this paper. We wanted to see in all these operating conditions that I'm showing here, what is the operation map. So what we have done here is just to see this solid mass flux as a function of the amount of pressurized gas that we have here. This VA that I'm showing here is a adimensional volume of pressurized gas that we use in this chamber here. Okay, so we can actually decrease or increase the solid mass flux in this unit by increasing the mass of solid inside this chamber. When we increase it, the mass of solid, the transport is going to be in a more dense transport, so the mass flux is higher. Or we can increase the pressure that we use for the transportation, and that one also can increase the solid mass flux. So we came up with what we call the operation map with all these conditions here. We have several experiments that we have done at IFP. And there was the operation map where this feeder could be operated. And that one is the region 1 that I'm showing here. The other regions, 2, 3, and 4, we could not operate them. The operation was jeopardized. In 2, we could actually work, but in this, for going to this high solid mass fluxes, we needed higher pressure, and we could not do it with this experimental rig. So if the experimental rig was capable of higher pressures, we could actually go here. But in regions 3 and 4, we could not actually operate. In 3, for decreasing the solid mass flux to this region, we needed a very tiny amount of biomass that was not feasible. It was very small, so experimentally was not easy to be transported. And region 4 was the opposite. It needed a very large amount of biomass in the system, and we know that when actually this one piles up a lot, the interlocking between the particles doesn't let the pressure to actually push them in, and the transport was not possible. So once we did this, this was just the operation map. We also studied we did some calibration and see how the transport works. Then we came to Barracuda and say, okay, let's see what the experiments, how do they compare with simulations. So we actually did exactly the same, almost the same conditions that we had here. The only one was the secondary air injection that we actually put as a boundary condition, but the pressure that was here, the pressure outlet, the amount of solid that we have put for this kind of physical properties was completely the same. So what we have done, once we started, we chose this experimental condition that I'm showing here, this one, and we started doing some mesh refining, selection of the different parameters. The first one was mesh refining. So here I'm showing how by increasing the number of cells, of course the time of the calculation was increasing, but we were also interested to see if there is time independency of the solid mass flux. We chose this 162 cells per cubic meter as the dimension of the cells, and that's in this region here. This was a good compromise between the calculation duration and also time independency. And we chose this one because we didn't want to refine it that much, because the simulations, we wanted to use it also for bigger scales. And for bigger scales, we wanted that the cell size is not very different from the smaller scale. So that's why we chose this one, and we started working on it. The region that the fast camera was located was here, so we placed a flux plane there, and for measuring the time that the biomass was being injected, and also calculating it with the simulation. So that was actually where we could compare the time of passage from experiments to simulations. Okay, once we chose our cell size, then we went to the main parameters that we usually use for doing the tuning and verification of our model. So it was the drag and particle-to-wall collision model. So for the drag, we used the 4 different drag models, the GDAS mode, so Venenu Ergon, Turton 11-speed, Hydron 11-speed, and EMMS. And as was also shown in different other papers, the EMMS for Geldart B and D, it looks to work better than the other ones, and we could see that the experimental solid flux compared very well with the drag model of EMMS. So that was the drag model that we chose. Another parameter was actually a normal and tangent particle to wall retention factor, and that was also, we wanted to optimize it, and this R is just the percentage of the solid that remains in the injection chamber after once all the biomass is transported. Experimentally, we were seeing 0.9% of the initial that was remaining. So when we decrease this parameter, it means that we increase the friction between the wall and the particle, so the more solid is going to be remaining inside the unit. So we chose a value of 0.7 that was giving us satisfactory results. Okay, so then let's look at the dynamics of the so just go on. This is just it's very similar to the fast camera that I showed, but no worries. I'm going to show the transient contours of the CFD here. Here, so we have the continuous region, which is colored by the pressure, and the particles are colored by their velocity. And you can see that the time scale is quite fast. Between 0 and 0.3, we have 0.3 seconds. We have most of the particles being pushed into the unit. So at the beginning, we have 500 kilopascal here. Particles are not moving. The particles start getting accelerated here. So you can see that the scale is 80 meters per second. So they're moving very fast here. But then just at this time here, the particles start decelerating because the pressure are actually getting much lower, and you can see that the scale of the pressure is also decreasing. We go to 40, 200 here, and at the end we can see that when most of the particles are pushed, there are just a little bit of particles that are remaining in our unit, and that's actually the remaining part that we measured and considered for comparison. And we published this one recently in Chemical Engineering Science. Just to do a comparison, I really like to do first qualitative and then quantitative comparison with the experiments. So here is the images that we had from our fast camera, and we wanted to see the hydrodynamics of motion if it was captured also by Barracuda, and that was the case. I mean, we had a very dilute region at the beginning with just the pressure release, and it was the highest amount of pressure on the left, but then we had a little bit here is very dilute, but here is just dense. And we were so pleased that this picture was actually used also for the front page of Chemical Engineering Science for July volume. So we were quite happy with the results and this paper. But then we went to the quantitative comparison. So in this slide, I'm just showing how solid mass flux as a function of the ratio between the volume of solid to the volume of pressurized air. And we can actually change this value, but by decreasing the pressure, so decreasing the solid flux, increasing the mass, increasing again the solid flux, and so on, or increasing both mass and pressure in order to increase the solid flux. And doing the experiment, between the experiments and simulation, we saw a very good comparison as for most of the conditions. And I just want to remind you that we tuned the simulations only for this condition here. The other ones are all extrapolated, and that was very, very, very encouraging. Also, the concentration of solid inside the the injection was also between the experiments and simulation quite very fair agreement, and also the time of passage of biomass, that was also between the experiments and the simulation quite well in agreement. So that was quite encouraging. So once we said that, okay, the model is working well with the parameters that we have chosen, now we can actually use it to go somewhere that the experiments could not actually work, okay? So we said, let's extrapolate it to conditions that we could not use experimentally. So here I'm just showing the solid mass flux as a function of the amount of gas that we have in the unit for different ratios of solid to gas. And first of all, we could see that increasing the amount of solid, so just going vertically here, we increase the solid mass flux, and that's because the transport is denser. But also we could see that at a certain point we had a maximum in the solid mass flux through the driving force, which was the amount of gas. And that we showed these 3 points here that correspond to these 3 images. And these images, they talk to by themselves. When we want to keep the ratio the same, we have to increase both the pressure, but also the mass, the amount of mass that we have. Up to this point, we have the increase of the solid mass flux, but at a certain point, there is the pressurized chamber is really full with solid, and this amount of solid gas that we have on the left part of the chamber is not enough to push the solid. So that's actually what I was talking about when I said that there is interlocking between the solids. Experimentally, was observed for an amount of gas that we choose. We show it with this VA star, which is just the amount of gas here in the left region, not considering the interstitial gas here. And 1.6 was actually where we could not operate anymore. The solid was not being moved. That was seen by Barracuda. It was also seen experimentally. The value that we saw experimentally was not 1.6, but 1.4, but we were very happy also with this phenomenon. We also saw extrapolated to other diameters, same operating conditions. We just changed the diameter of the injection from 2 centimeters to 12 centimeters, a very nice and robust operating conditions we could see between different diameters. So the solid mass flux for the same conditions of VS on VA was actually being obtained. So this injector is actually can be scaled up to higher diameters. We are now working also on smaller diameters because it's of interest for our lab units. Okay, just to conclude, the hydrodynamics of the pressurized feeder was characterized experimentally. MPPIC was tested and compared with selected experiments, and then by using these drag law and particle wall interactions that we tuned, we used the model to study the feeder hydrodynamics in other operating conditions. The feeder performance was maintained for injectors higher with a larger diameter than 0.2, and the model will be used further to study the biomass penetration in the fluidized. That's what we are working right now. So I would like to just thank you all for your attention, and if you have any questions, I'm happy to answer.